will be looking into the number system. So number system that tells us how can we store or represent numbers in a digital system. So this is a very important part because this will tell us how can we do processing over those numbers and all, and what are the limitations and what are the advantages that we can get of different number systems that we can think about, or what are in general the number systems that are available in a computer, or say for the sake of simple mathematical interest also you can look into this topic, which will be telling about different ways in which you can represent numbers. So any number system that we look into, so it will have two important components in it. One is called the base of the number system. So where we talk about some quantity that we represent, like how many digits can be there, how many symbols can be there, different types of symbols, and the other part is the symbols. So any number system that we talk about, so these are the two things that you have to tell. So you have to tell me a base. So as soon as you tell me a base, we can assume that there will be so many different types of symbols that you can have. Now a number system may be consisting of different number of digits. Like I can have, say, a decimal number system where base is 10. So as soon as we know that the base is 10, we know that there are 10 symbols, and those symbols are conveniently represented as the say 0, 1, 2 up to 9. Okay. So if you are talking about a binary number system, the base is 2. And in that case, the symbols, only two symbols are needed. So we represent them as 0 and 1. So, there is of course some value associated with this. So the convention that we follow is that in a decimal number system, so 0 represents the integer value 0, 1 represents the integer value 1, and similarly the 9 represents the integer value 9. In a binary number system, the base is 2. And the symbols that we have are 0 and 1. So here also we have got the assumption that 0 represents the integer value 0, and 1 represents the integer value 1. In an octal number system, base is 8, and naturally there will be 8 symbols, and we have got the symbols 0 to 7. Hexadecimal number system, the base is 16. Now here is the problem, because so far whatever we had, so we have sufficient number of symbols to represent individual values of the symbols. Now we don't have that. So now you see that up to 0 to 9 we take. So these are the 10 numbers that we have. After that, so we don't know any symbol. So what is done is that this A, B, C, D, E, F, so they have been taken as symbols. And here actually comes the thing that I was talking about, the value associated with the symbols. So this A, it is associated with the value 10, the integer value 10. Similarly this B, so this is associated with the integer value 11. So C associated with integer value 12. That way F associated with integer value 15. So you can say that instead of this A, B, C, D, I'll be using some other notation, alpha, beta, gamma, delta, like that. So there is nothing wrong in using some different notations for these symbols. But what is required is that you have to tell what is the corresponding integer value for the symbols. Otherwise, you will not be able to represent the some quantity in that number system. Okay. The next thing that we need to know or need to understand is, like, whenever you are representing some number, so you have to tell how many digits are you allowing for the numbers. Like if I say that I have got decimal number system, okay, so as soon as I say decimal, so I know that the digits that I can have are 0 to 9. The next question is how many digits I can use, how many digits for a number. So if we are trying to say that, so if I say that I will be using 3 digits, so you can say as if I have box like this, and in this box, so there are 3 places. Okay, so in the first place you can put a digit, say 2. So here you can put a symbol 2, here you can put a symbol 5, here you can put a symbol 9. So as soon as I limit this value to 3, So you can understand the maximum value that I can have in this system is 999, not more than that. So I can this system can represent numbers from 0 to 999. So this number of digits that we are using for representation, that is vital. So whenever we are talking about so these computers or the processors, we see that it is a 16-bit processor or 32-bit processor. So essentially what it means is that the information that it can handle, the size of the data that it can handle as the basic processing unit. So that is going to limit the number of digits here. So going back to the point that we were discussing, so we have got these number systems, their base values and their symbols are like this. Then we can say answer like whether they are used by human or not. So of course this is a bit tricky, like somebody may be very comfortable with hexadecimal number system and maybe always writing in terms of the hexadecimal digits. So that is very much possible, but normally it is not so. So from our school days we are familiar with decimal number system, so we say that it is used by humans, where the others, binary, octal and hexadecimal, are not. Okay. Then they are used in computers. So decimal number system is not used in computers, and then we can have this binary number systems used, octal and hexadecimal number system. Now you see that while talking about this, one thing I have purposefully avoided, where can we have a number system with base 1? Okay, so that we have not talked about. So answer is definitely yes, we can have a base 1 number system as well. So here if I say it a base 1 number system, so that is a unary number system. So since base is 1, so I can have only a single symbol. So number of symbols that you can have is equal to 1. So if I decide that the symbol that we will be using is also 1, then if I ask you to represent 10, the quantity 10 in this number system, then what you will do? You will write 10 such ones. Fine? Because I don't have any other symbol, so as many value I want, so I needed a quantity 10 to be represented, so I put 10 such ones. If I need to represent the quantity 0, so I don't put any of these things, so none of the ones are there. So if I want to represent 5, then 5 such ones are there. So this is unary number system. So it can be used, but this is not used because of it does not make it amenable to the processing that we have possible with other numbers, unary number system. Okay, so in our discussion, so we'll be concentrating mostly on these number systems, and so this decimal number system. So if we say that quantity is 0, 1, 2, 3, 7, so the 0 in binary will be represented as 0, in octal also 0, hexadecimal also 0. 1 will also be represented same, but 2 onwards there will be problem, because 2 cannot be represented by the symbols of binary number system. So I need to use 2 symbols, 1, 0 to represent 2. Similarly, once 2 is done, so 2, 3, so they can be represented by binary number systems. Then octal and hexadecimal, they don't find problem till 7. Okay, so we have got enough symbols to represent the numbers. But after that, of course, the problem starts coming. Like octal faces problem from 8 onwards. So 8 has to be represented by 2 symbols, 2 digit like 1, 0, 9 by 1, 1 like that. So that way till 15 hexadecimal does not face any problem. But if you are going to 16, then of course hexadecimal will have to have 2 digits now. Okay, so this will be 16. So that way it will grow. So this way these numbers or the quantities, they will be represented in different number systems. So this talks about the conversion between the bases. Okay, so these are the possible conversion, like all these number systems we can convert from one form to another form. So decimal to binary, binary to decimal, decimal to octal, octal to decimal. So like that we can convert between these number systems very easily. And so ultimately in a computer system, so it understands the binary number system. So there of course it does not have any bearing. Other number systems it does not have any bearing. So truly speaking, if we are learning about this digital circuit class, so digital circuit course, we don't need to learn about the other number systems. Okay, so that is just for our understanding of the binary number system. So truly speaking, so if we know the binary number system well, so we are done. We don't need to know others. But because we are familiar with other number systems, so we will be looking into their conversion to make us feel comfortable with the number system. So 25. So 25. So normally while writing the numbers, so we don't write this base part. When because in our day-to-day life or from our school days, with the numbers that we know, they are all base 10 number system. So we'll be but if you want to make it explicit, then we do it like this. After the number, at the suffix we write the base. So this 25 to the base 10 is equivalent to 11001 to the base 2. So in a binary number system, so it is 11001. It is equivalent to 31 to the base 8 octal number system, and it is again equivalent to 19 to the base 16, that is hexadecimal 19. So all these numbers are equivalent. So we will be looking into some conversions from between these number systems. To understand this conversion process, so we will be looking into the conversion of decimal to decimal, like decimal numbers, how is it converted to decimal. So this will give us the understanding. So you see that we are not going to so decimal to decimal conversion as such is meaningless, but this will just give us a recapitulation of our school days knowledge about how these numbers are actually representing some quantity. So in this in a number like 125, there are 3 digits, 1, 2 and 5, but all of them are not representing values of equal strength. Okay, so the number 5, so when you are looking into the number 5, so actually it is representing the number 5 into 10 to the power of 0, that is equal to 5. So this 2 here, so this is actually representing 2 into 10 to the power of 1, that is 20. And this 1 here is representing 1 into 10 to the power of 2, that is 100. So the symbol that we have, so the value of it multiplied by the some weighted value of the base. So that is going to be the contribution of a particular digit. So a digit is, so whenever we are talking about a digit, so digit contribution is equal to the value of the digit, value of it multiplied by base taken to the power of the position of the digit. So this is the overall formula that we are getting. So this is digit contribution is value of it multiplied by base to the power of position of the digit. So this position is 0, so its contribution base to the power 0. This 2 is at position 1, so this is 10 to the power 1, and this 1 is at position 2, so it is 10 to the power 2. So this weight varies with the position. Okay, so next we will look into, so this will tell us like how do we do the conversion. Now when we are converting say binary to decimal, so that the technique that we have to follow is multiply each bit by 2 to the power n, where n is the weight of the bit. As I said that any number, when you are trying to get the value of a contribution of a bit or a digit, it is the value of the digit multiplied by weight of the digit, and the weight of the digit is coming from the base to the power n, where n is the position of the digit. Now in case of binary number system, so we have two symbols possible, 0 and 1, and anything multiplied by 0 gives 0 only. So we can say that okay, it is so we can just write it, multiply each bit by 2 power n. So this weight is the position of the bit starting from 0 on the right, and then add the result. So here is an example. So this is a binary number. Okay, so 6-bit binary number. So this is the bit 0. Okay, so this 1 into 2 to the power 0. So that the position 0. Then 1 into 2 to the power 1. Then 0 into 2 to the power 2. So that way it is growing. So if you just get the corresponding contribution, so this is 1, this is 2, this is multiplied by 0, so the contribution of the bit 2 is 0. Then contribution of bit 4 is also 0. Others are contributed to some value. So that way it gives 43 in the decimal number system, because these values that we are taking, so they are the decimal values. Okay, so since they are the decimal values, so that is ultimately giving me a decimal number 43. Now in a similar line, so we can convert octal number to decimal number. So multiply each digit by 8 to the power n. So in case of octal number system, so base is 8. So we multiply each digit by 8 to the power n, where n is the weight of the digit. And again the same thing, that weight is the position of the digit starting from 0 on the right, and then we add all the results. So this is 724 to the base 8. So 4 into 8 to the power 0, that is the contribution is 4. 2 into 8 to the power 1, contribution is 16. 7 into 8 to the power 2, the contribution is 448. So you sum them up, so it becomes 468. So that way we can convert this, we can convert an octal number into a decimal number. Hexadecimal to decimal, again the similar way we can do, multiply each digit by 16 to the power n. So base is 16, so we take it to the power n, where n is the weight of the digit, and then we the weight, so that then we just add the results. So in a similar way, so ABC to the base 16, so 6C into 16 to the power 0, and the value of C is 12. Okay, so that, as I said, that each symbol, it has got some corresponding integer value in the number system. So, and for hexadecimal number system, so A is 10, B is integer value is 11, and C's integer value is 12. So that way, so these values are multiplied by the powers of 16. So that way we get the value 2748. So this is the corresponding decimal value for this ABC to the base 16 in hexadecimal system. Okay, so that way if you want to go to the decimal, so you can do it in this fashion. So you can multiply by by the weight of the base, and then we can go to the decimal system. But the other side, the decimal to binary, octal and hexadecimal conversion, so that for that we need to divide. Okay, for decimal to binary, if you want to convert, so you can convert into, we can divide by 2, and we can keep track of the remainder. So the first remainder is bit 0, second remainder is bit 1, etc. So for the sake of understanding, if we think about a decimal to decimal conversion, how do we do this thing? Okay, so we have seen by multiplication technique, but you can if you think about this decimal to decimal conversion, say the number, say 567. Okay, so 567, so I am looking for decimal to decimal conversion. So what it says is that you divide by the base of the number system. So if you divide this 567 by 10, so what you will get? The value 56, okay, as the quotient, and the remainder is 7. Then you divide again 56 by 10. So what you get is 5 with remainder as 6. And what this 5 divided by 10, so you get this 0, and the remainder is 5. Now what you do for getting the converted form, so you just write down these reminders from this side. Okay, first reminder, the latest reminder is 5, previous to that 6 and previous to that 7. So this is the way we are converting the numbers. Okay, so same thing applies to any other number system. So this is with respect to decimal. So you can do it with respect to any other number system. So we'll see that while we are converting from decimal to binary. So since in binary system the base is 2, so we'll go on dividing by 2 and we'll track the remainder value. Say what is 125 decimal to binary. Okay, so you divide 125 by 2, so 62 is the quotient and 1 is the remainder. So we divide again 62 by 2, so you get 31 as the quotient and 0 as remainder. Divide 31 by 2, you get 15 as quotient and 1 as remainder. Divide 15 by 7, 15 by 2, get 7 as quotient, 1 as remainder. Divide by 2, 3 as quotient, 1 as remainder. Then again divide by 2, get 1 as quotient and 1 as remainder. Again divide by 2, the quotient becomes 0 and remainder is 1. So at this point we stop. Similarly what we did in the decimal number system, we do the same thing here, and so we get this. So now we start writing from this side. So this 1 1 1 1 1 0 1. So this is the thing. Okay. So this is the conversion. So this way we can convert a decimal number into binary number. So if we looking for other way, the octal to binary number system, so conversion. So one thing that you can do is octal. So you can come this way. So you can convert this octal to decimal, and then from decimal you can come to binary. So this is one avenue. Other straightforward avenue for octal to binary conversion is you can do it some sort of grouping of bits, because in octal system the base is 8 and in binary system the base is 2. So you can group 3 bits of binary numbers. Sorry, you can convert each octal digit by a 3-bit binary number. And because of this, the divisibility of these two bases, of this base 2 of binary and base 8 of octal, so this octal digit boundaries are similar to this binary number boundaries. So that's why. So this each octal digit will form a 3-bit boundary for the binary number system. So you can convert octal to binary. So you can directly convert individual digits of this octal number system into binary number and get the result. So what is 705 to the base 2? So 7 is 111, 0 is 000 and 5 is 001. So you can get it like this. So or other way you can say that okay, I can convert it in the so 705. So if you convert this 705 to decimal, so you will get 7 into 8 to the power 2 plus 0 into 8 to the power 1 plus 5. So it is 64 into 7. Okay. And so it is 64 into 7. Yeah. Okay. So this is 448 plus we have got this plus 5. So that is 453. Now this 453. So this 453, as I was telling, so you can convert it into binary. So this is 22, 13, that is 6, so 1, then 2, 1130, then 2, so this is 56, 1, then 2, 28, 0, then 2, 14, 0, then 2, divide by 2, 7, 0, remainder is 0. So this is 3, 1, this is 2, 1, 1, 2, Okay, so then we have to write in this order for the conversion into binary. So this is 111 000 101. So either you can do it like this, so you can take these individual digits and then convert them directly into 3-bit binaries. So you can get it directly from octal to binary, or you can just you can convert to decimal number system, and then from the decimal number system again divide by 2. So it's a slightly longer way of doing it, but that we are doing it for the sake of our confidence that okay, this method is correct. Okay, so next we'll look into this hexadecimal to binary conversion. So here just like the octal system, so we took 3 bits, each octal digit was taken separately and they converted into 3-bit pattern. So here also we will be taking the individual hexadecimal digits and then convert it into 4-bit equivalent, because that hexadecimal 16, so that can go, it can represent values from 0 to 15, and we will need 4-bit for representing this 0 to 15 in the binary number system. So the same thing, that is suppose 10AF to the base 16. So what is the value in the binary number system? So you can just take the 4 digits and then convert them into binary numbers, 4-bit binary numbers, and that is the result. So you can just verify this by doing the similar exercise, that is converting this into decimal and from decimal converting it into binary, but that's a lengthy process, so we are not doing it. Of course, you can say that okay, these 0 0 0, so these 3 zeros are not necessary because they are the leading zeros and they don't have any contribution to the overall value of the number, so you can ignore them. So but this is just for the sake of completeness, so it has been done like this. Now how to convert decimal to octal? Okay, so just like decimal to binary, we divided by 2 and kept a track for the remainder. So here also we do the same thing, we divide by 8 and keep a track for the remainder. So this is 1 2 3 4 to the base 10, converting to hexadecimal octal number system. We divide by 8, so remainder is 2. Proceed another step, remainder is 2. Then another step, remainder is 3, and then another step, so remainder is 2. So the number that we get is 1 2 3 4 to the base 10. The decimal number is basically 2322 to the base 8 in the hexadecimal number system, in the octal number system. So in this way we can convert between the number systems and by dividing by the base of the number system, and keeping track of the remainders.